Okay, so number one, sorry, I had to grab a calculator. Number one is number one and two are analyzing exponential functions for behavior and sketching the graphs. So the first thing I want to do is think about one third to the x minus 3. So in general, the exponential functions look like this, and unless there's a vertical shift, they have a horizontal asymptote at y equals 0. Well, in this case, this has a horizontal shift down 3. So I know before I graph it that I'm going to have a horizontal asymptote at negative 3. Now, if you're unsure of this, that's okay. You can still use the table to figure it out. So if you want to plot the function, the first thing you do is go to y equals. And you've got 1/3 to the x, and then minus 3. If you want to look at the graph, you can. You can kind of mimic the window, negative 6 on the x, 6 on the x, and then negative 4 and 30. No, just kidding. Scale is 1. Negative 4 and 30. And you can kind of see what your graph should look like. So I should start from up here, come down, and then level off. And we're going to be leveling off at negative 3. And you can know that for sure by going to the table. And I noticed that in the negative direction, at negative 5, I'm at 240. I can't see 78. But I can see that at negative 3, I'm at 24. So at negative 3, I'm at positive 24. And then at negative 2, I'm at 6. At negative 1, I'm at 0. Negative 1, I'm at 0. At 0, I'm at negative 2. And then negative 2.6. So this is negative 2, negative 3 is right there, so somewhere in there. And then basically what happens is that you just get closer and closer to 3. It says negative 3, but you're not actually there. If you actually look at it, it's over to the right. It's not quite there. So the best thing to do is to just kind of sketch a curve going through the points. Go kind of basically just lay on the horizontal. It's okay if you're actually on top of it. I don't mind that. What I don't want is you going below it. Okay? You do need to label. This is a horizontal asymptote at y equals negative 3. And so looking at the graph after I've sketched it, it says growth or decay. Well, I already knew it was decay because of this number right here, but if you look at it, it is going, starting from infinity and going down. The rate of growth or decay has to do with this, rewriting it as an initial value times 1 plus or minus the rate to the x, and then plus maybe a vertical shift. Okay, this is your rate, and that's how far away you are from 1. So I could rewrite 1/3 as 1 minus 2/3. So basically think 1 minus what is 1/3. So if you need to solve for that, then you would just subtract 1 and then divide by negative, and you'd get negative 2/3. So, well, you get a positive 2/3 because the rate is just 2/3. But when we were doing it in the homework, we tended to write it as a decimal. So you would write it as 0.66 or 0.6 repeating, whatever. And then you could just say that is 66.667 if you want to give yourself 3 decimals, but percent. Okay? It's a decay at 2/3 percent. Well, I guess 2/3 only. 66.7%. Okay, domain. Domain is left to right, so it does go all the way to the left and it does go all the way to the right. If you were to scroll on here, there would be no error messages. It would always have a value for the x, or for the y values given any x. So the domain is all real numbers, or negative infinity to positive infinity. But range is low to high. So even though it starts up here on the left, it starts up here at positive infinity, the point is it's low to high. So the lowest you go is negative 3, and the highest you go is infinity. You can't reach infinity, and in fact, we don't reach negative 3. Even though the table says we do, we don't, okay? You can get closer and closer and closer to it, but you never actually reach it. So in behavior, it's talking about as you go to the left and as you go to the right, what your function's approaching. So as I go to negative infinity, and as I go to positive infinity, and guys, I will be counting off if you do not use the correct limit notation. The x goes to infinity goes below the limit. Stephen is not the only one. Stephen is by far not the only one. Okay? You better use the correct notation. LIM, x approaches underneath it, y equals. Okay? So, as I go to the left, when x approaches negative infinity, so when x approaches negative infinity, so when x is going this direction, the function is going up to positive infinity. And as x goes to positive infinity, as x goes to the right, the function is approaching negative 3. Your horizontal asymptote will always be one of your end behaviors, depending on left or right. Okay, x-intercept. So x-intercept crosses the x-axis, and our x-intercept was actually one of the points on the table, so it is the point -1, 0. The y-intercept is also one of our points, which makes it easy, 0, -2. I think you're going to read that. Okay, the asymptote, we already labeled that, but we'll go ahead and write it again. It was a horizontal asymptote, and it was y equals -3. You at least have to have the y equals -3. Because if you don't tell me horizontal, but you tell me y equals, I'm going to assume it's horizontal, because that's the only kind of function a y equals is. Well, a y equals a number. Okay, and then average rate of change on -2 to 2. So average rate of change is basically slope. What I'm asking you to do is on the interval from -2 to +2, I want you to find the slope between these 2 points, which is just rise over run, change in y over change in x, yes? So keep in mind that these are 2 x values, x1, x2, and if you want to find, well, let's see. I'll do this. If you want to find slope, you've got to have 2 coordinate points, which means we need the y values. So I'm going to go back to my table. I know that at -2 I'm at +6, but at +2, okay, so at +2 it says 2.8 repeating. So I'm going to go ahead and put 2.8 repeating, and whenever and when I use it, I'm going to use a lot of those decimals, because one thing that a lot of people ran into on the homework that lost them points was that you have to be correct to 3 decimal places, but you guys only use 3 decimal places whenever you were finding it. If I'm finding the slope and I need the y values plugged in right here, I'm going to put in 5 or 6 decimal places so that whenever I do the final estimation, I am correct to 3 decimals on my final answer. Does that make sense? If you put 3 decimal places for everything in here and then you do the estimation and you've rounded, you're probably not going to be correct to 3 decimal places for the final answer. So be very careful about that. So y2 minus y1 is, so change in y over change in x. Now, order doesn't matter as long as they're the same. So I'm going to change, y2 is -2.8 repeating. And like I said, I'm going to be writing in probably 5/8 because I want to be accurate, my final answer to be accurate to 3. So y2 minus y1, so -6 over x2 minus x1. Okay? So be careful about plugging those in. y2 minus y1 over x2 minus x1. So if you want to do the fraction bar, make it easy. Press alpha y equals and then press enter. So -2.88888 minus 6 divided by 2 minus a -2, or 2 plus 2, and you get -2.222, and that is my average rate of change on that interval. Okay? Alright, on this one, I've got 5 times 1.5 plus to the x plus 2. This number, which is the number being raised to the x, is greater than 1, so I already know that it is growth. But I will go ahead and type it in. 5 times 1.5 raised to the x plus 2. Okay, I'm going to go to the table. And I'm going to go to the left first to see what's going on. And I see that, okay, my vertical shift is 2. So I know that that's where my horizontal asymptote is going to be. So horizontal asymptote, y equals 2. I'm going to go ahead and put that down here. Okay. Okay. Yeah, I'm just turning. Okay. And now I need to plot points. So I know at negative At negative 8, I'm at 2.13. I'm going to start at 0 and then work my way there. Okay. At 0, I'm at 7. At negative 1, I'm at 5.3, so there's 5, so 5.3. Somewhere in there. At negative 2, I'm at 4.2, so somewhere right there. Closer to negative to 4. At negative 3, I'm at basically 3.5. So that's 3.5. And then basically at 3. And then at 2.5, or a little over. And then 2.4. So I can tell that it is approaching 2 on this side. So I'm just going to go ahead and do that and draw an arrow. And then I go to the right. So at 1, I'm at 9.5. So there's 9, 9.5. At 2, I'm at 13.25. So there is 13.25. Yes. Yes. At 3, I'm at 18.8, so almost 19. Which I basically put at 19. And then 4, I'm at 27. That's probably going to be the most I can see. 27.3, so a little past 27. Close enough. Okay, so connect the points as best you can. And draw arrows at the end. Okay. So when I think about the rate, remember this is the same thing as saying 5 times 1 plus or minus something to the x. So it's plus 0.5, which means our rate is 0.5 or 50%. Okay? It's how far away from 1 it is. And so 1.5 is 0.5 away from 1 in the positive direction. Domain is from left to right, and domain of exponential functions is always all real numbers. Range, however, is limited by the horizontal asymptote, so the lowest it goes is 2, and the highest it goes is up to infinity. The end behavior, as I go to the left, what's the function approach? And as I go to the right, what's the function approach? So as I go to the left, the function is approaching the horizontal asymptote 2, and as I go to the right, the function is going up to infinity. So like I said, your answers will always be either infinity or the horizontal asymptote. Okay, x-intercept, where we cross the x-axis. Well, I have this horizontal asymptote that I can never go past, and the x-intercept is the x-axis is below it, so I'm thinking none. Now the y-intercept is where we cross the y-axis, and I remember that point, that's when x equals 0. So even if I just plugged it in, 5 times 1.5 to the 0 plus 2, 1.5 to the 0 is just 1. 5 times 1 plus 2 is 7. But I also remember it as being 0, 7. And then average rate of change on the interval from 0 to 3. So we're finding the slope between this point and this point. So we're finding the slope between those two. It should be a steep positive. Okay, so remember, these are x's, 0 and 3. That's x1, that's x2. And I want the y value. So I'm going to go to my chart, and I know that, or my table. At 0, I'm at 7. And at 3, I'm going to go ahead and go down there. Oh, it is exactly 18.875. So y2 minus y1 over x2 minus x1. So y2 minus y1 over x2 minus x1. So 18.875 is 11.875. And then divided by 3. And my answer is 3.958. And that is my slope, my average slope of the curve between those 2 points. Okay. On number 3. It says, use exponential growth and decay to solve each problem. A $25,000 card depreciates 9% each year. When will it be worth less than $5,000? So that's the amount equals initial amount times 1 plus or minus the rate to the time. So the initial amount is 25,000 times 1 minus, because it depreciates, 9% is the same thing as 0.09, so minus 0.09 to the t. And it says when, so I'm trying to find the time value, will it be worth less than 5,000? So I guess find out when it's worth 5,000 and it'll be less than that, or past that. So I want to know, when does the amount equal 5,000? I guess I could just say 0.91 at this point. Or 1.09. 1 minus 0.09. Okay. Now, technically, you could solve this by hand now, because I've taught you about logs and exponentials and their inverse relationship. But I'm going to go ahead and do this with a calculator. 5,000 and 25,000 times 0.91 raised to the x. And I'm going to want to know when these two functions meet. So I have to remember window. X represents time. So when I think about time, I don't think negative, and I don't think that it's going to take 50 years. But I'm going to go ahead and do like 25 years and call it good. If I need more, I can do that. Y is money. So 0, I need to be able to at least see 25,000. So I'm going to go 30,000 and press graph. Okay. So at this point, I just need to find the intersection, so second calculate number 5. And it says first curve. If you have more than two functions in here, then you have to actually care about first curve, second curve. You can hop around up and down to get from curves. But if you just have two functions, you're trying to find the intersection, just enter, and there you go. So we're talking 17.065 years. So after that, it will be worth less than 5,000. Okay. And that is page 1.